This is podcast 10.4, talking about how to write net ionic equations. And this is going to be filling in page 9, just the bottom part that we didn't go over in the last podcast. And we've already technically done half of it. I'm just going to kind of explain it. So, shouldn't be too bad. I do need you to find your solubility chart that we went over in the last podcast, and hopefully it's notated, because that's how we're going to be starting off each of these problems, is with the same stuff that we finished with last time. In fact, I'm going to look at that last problem from the last podcast. It asked us to write out and finish out that reaction, the blue part. So predicting the products of a reaction, balancing it. And then it just asked us to circle the precipitate that should form. When we write a net ionic equation, the only difference we're going to start off the same way with writing and balancing that equation, finding our states of matter. Anything that is insoluble is our precipitate. And the net ionic equation is just writing an equation to form that precipitate. We're going to go through kind of more of a proof process to back up that answer, and so it's going to be a whole process. But in the end, in order to find a net ionic equation in this situation, this problem, we're forming this solid, this calcium phosphate. Notice I have 3 calciums and 2 of these phosphate ions. The net ionic equation to form this solid is going to come from those specific ions. I'm just going to say I have 3 calcium ions and 2 of those phosphate ions. And each of those technically would be marked as aqueous because they're ions, but that's the net ionic equation for this reaction. So that's going to be one of the pieces that we're doing. And that's really the main goal, is to get there. But along the way, we're going to be getting a couple of other things. Each of these questions is going to ask for these 4 specific things because they are all related. And this is technically your process, your steps for working through these problems. First step, find the balanced equation. Second step, use that and turn it into what's called an overall ionic equation. And from that overall ionic equation, we can be sure that we have the correct net ionic equation, which we could probably see and understand from the initial reaction, but this is kind of proof on how to get there. And then to identify those spectator ions, the stuff that's left over. So that's our process. And like I said, every single question is going to look something like this one, where it specifically asks you to do all 4 of these steps. If it doesn't ask you for these 4 steps, don't do these steps. There's always easier ways to get to that answer if it doesn't want you to go through it. But kind of like in geometry, sometimes you got to prove why it's happening the way it's happening in your answer. And so this is kind of a proof of how we form that precipitate. So I'm going to start by going over this example. I'm going to give you a lot of details and kind of explanations, and I want you to just pay attention to how I work this first problem out, and then I'll go over those same steps, review those, and give you a second to write those down in some of the blank space, because I know there's not really any instructions on your page, so we are going to get some instructions and steps written down. But for right now, let's go over this first problem. This first example problem that's written out for you says that we have solutions of potassium sulfate and barium nitrate. So first unpacking that. We've got potassium sulfate here, and remember when we write compounds that we have to cross-drop reduce the charges. So I'm looking at my potassium, which is in the first column. It has a +1 charge, getting with this sulfate, and because that's sulfate, not sulfide, that is from the back of the periodic table, kind of next to that solubility chart, and this tells us that sulfate is SO4 with a -2 charge. Now, because those charges don't match, we got a +1 and a -2. If it was +1 and -1, we just shove them together and be done. Because they don't cancel out exactly, we have to cross, drop, reduce. We don't have to write that 1, but we do have to write the 2, which is how we got this K2SO4. Now, next we have that barium nitrate, and barium is a +2 charge because it is in the second column. Nitrate also ends in 8, so that's a group on the back of the periodic table, which has a -1 charge. Once again, they are not canceling. It's a +2 and a -1, so we're going to have to cross, drop, reduce, which is why that 2 came over onto the nitrate. Remember, we had to put that in parentheses anytime we put a number on the outside of a group. Now, our next step, after we have the formulas for what stuff we're starting with, is to go back and predict the products. So, with double replacement reactions, you need to remember that the first substance that we have, we're going to take the first substance from the first ion from the first substance and combine it with the second part of the second substance. So they're switching partners. This is that wife swap situation. And so we get potassium and nitrate getting together. And if you take a look when they were over here, potassium as a +1, nitrate was a -1. They still have those same charges. They're just together now. And +1 and -1 canceled out, which is why we just had KNO3. I'll explain that too up front in just a moment, but that's nothing related to these charges in the compounds. That was balancing the equation. Then barium sulfate, the leftover bits, get together. It's just important to make sure, because barium was at the beginning of its formula here, it still needs to be at the beginning here. So barium and sulfate get together, and notice this is a +2 and a -2. So those do cancel out and make just BaSO4. So all of this so far has been technically review, hopefully, on how to write and balance a chemical equation. The balancing part is what I alluded to before. This 2 over here is because when I wrote these formulas, I had 2 Ks and 2 NO3s, so I have to make sure I have 2 Ks and 2 NO3s on the product side as well. So that's all I needed for balancing purposes. Then I have these states of matter. When I looked at my solubility chart, just like we did last time, we identified that if something was soluble, we mark it as aqueous. A quick little kind of hint or cheat, you don't have to check your reactants, because this question already told us that it was solutions of potassium sulfate and barium nitrate. So solutions are always going to be aqueous. They're already telling you it's dissolved. So I already know these are always going to be aqueous. I just need to check my products. And when we're checking those, remember to start at the end, SO4. SO4 is at the bottom of the soluble section, but barium is one of its exceptions. So this is insoluble, and we mark it as a solid. Potassium nitrate is soluble, aqueous, because nitrate is always soluble. There's no exceptions. So we got all of our chemicals written out, states of matter on there, and it's all balanced. It's a lot of stuff, but that's going to be the basis for everything else that we're doing. So in our overall ionic equation, what we need to do is break up anything in the last reaction that was aqueous. And so everything but this barium sulfate is aqueous, which means it's all breaking up. This is going to be the longest one, but it's not really anything new. We already found all of those substances, and I'm actually going to have that slide come back so that I have all of the charges there. Once these compounds break back up, you're going to be able to see the charges on each of those ions. So, first aqueous substance that I see is potassium sulfate. We're going to break that up into the potassium and the sulfate part, and the potassium is going to have that same +1 charge. You don't always have to write the 1, but I like to. It's still aqueous. And notice the subscript that we had here, this K2SO4, turned into a coefficient. And we do that because those Ks aren't actually connected together. This is a simplification, but they're both basically connected to that sulfate. So when this dissolves in water and those ions break apart and these bonds break, then those are going to be forming 2 separate Ks and 1 SO4. The SO4 stays together. That's one of our polyatomic groups. But any of those subscripts that are not part of a polyatomic are going to come to the front and form a coefficient. So we have 2 K pluses and 1 SO4 with a -2 charge. Then we have our barium nitrate. And notice here, barium has a +2 charge and it's aqueous. Then I have those 2 nitrates, once again bringing that subscript up front into a coefficient, and giving it its charge. And then I have my barium sulfate. That was a solid, so I am not breaking it up. It stays together. And then I have another aqueous here, potassium nitrate. going to break up into potassium and nitrate. And this time notice that if I have a coefficient, it's going to distribute to both of those substances, because if I have 2 potassium nitrates, when this breaks up, this potassium and those nitrates are going separate ways, and you can clearly see here that it'd make 2 Ks and 2 NO3s. So that's how we write out the full net ionic equation, just going through and breaking things up. And if we've already written these out, I know that seemed like a lot of work before, but if you write that down, you got a leg up on that next step. Now, from this overall ionic equation, it's all about finding this solid. So I'm going to clean this up just a little. And if we're looking for this solid, the solid is always going to be your one and only product in your net ionic equation. And your reactants it's only going to be the ions needed to make that product. So to make barium sulfate, I needed barium and sulfate. So those 2 things came down just like we wrote them in that overall net ionic equation. So we're really just pulling this apart into 2 pieces. The stuff that makes the solid comes into the net ionic equation, and then everything else that didn't come and be part of the net ionic equation is what we call spectator ions, because they really didn't do anything in this reaction. Look at them. They're just sitting there before the reaction. They look exactly the same as the other reaction. I guess they maybe walked around a little bit, moved around, but they're not actually changing in the reaction, so we call them spectators, just like in a game. There's some people that just walk around and watch what's happening while everyone else does the hard work. So there's the same thing on before and after. You don't have to have the numbers of them. They don't really matter. We just want to know what is a spectator. Now, why spectators matter is really because they don't matter. If I was doing this reaction, I'm like, darn it, I don't have any potassium sulfate, but I do have sodium sulfate. I can do the same reaction. I'm going to see everything happen exactly the same because that potassium is not actually taking part in the reaction. As long as sodium is still a spectator, and it will be, then the reaction will proceed the same no matter what spectators are there. They're just hanging out watching. They don't affect the game. So that gives us a little bit of power to understand what the core of a reaction is, and gives us a little bit of kind of flexibility with how we get that reaction done. So that's our process. And technically, if I wrote down every single thing that I just talked about here, it would take up a lot of space. Feel free to write that out, I guess, if you maybe have a separate sheet of paper, if you need to. I don't think you can squeeze it in that little space that you have up above and kind of beside this example. But really, that first step is not really necessary for you to break it up and summarize all of that, because that's mostly stuff you should know by now, is how to write out and balance an equation. Feel free to write as much of a reminder as you need, but don't write any more than you need. And technically, a lot of these little A, B notes are the same thing. It's just like, hey, make sure you have the states of matter and their charges, and double check that you've gotten all the little pieces there. So if you don't need those little reminders, then this breaks up into some pretty manageable steps. And those steps really do come back to those same 4 initial steps that I showed you, the parts that are always going to be involved in these types of questions, and then a brief, single sentence on how to do them and what kind of thing you're doing. So I think this is probably all you need, but some of you might need a little bit more help in remembering all of the different pieces of these. So write as much or as little as you need, but get that down, and then we are going to work this next problem together. But I want you to kind of look at your steps and make sure that it can get you through this problem as we're working it out. So pause it, go back to whatever instructions you wanted to write down, and make sure you have some kind of steps written down there. I do expect to see some kind of instructions because I didn't really give you many on my own. Okay, so I'm going to focus on these first 2 steps because this is where most of the action happens, and then we're basically going to transfer that stuff onto the next 2 pieces, breaking that up. So first step, writing out the balanced equation. And I'm going to try and color code things to keep them straight, help you follow along a little better. But writing our equation, this is silver acetate. So this is my silver, and remember, it is one of those silly transition metals, and most of those have multiple charges, but silver is always a +1. Acetate is probably most people's least favorite polyatomic, but it does have that 8 at the end, which tells me that that is on the back of the periodic table, and I prefer the first version of that formula. So these are my two ions, and the nice thing is it's a +1 and a -1, so those just cancel out. So my silver acetate goes here, just both of those together. And then it says that I'm combining this with strontium chloride. So strontium is in the second column of the periodic table, means that it has a +2 charge. Chlorine has a -1 charge. They do not match, so we have to cross-drop reduce. And that's going to form, I'm going to leave a little bit of space just in case I need to balance that. And the plus can be blue. So strontium chloride there. And now I have to predict our products. So I'm going to take the first thing from the first chemical, so that's going to be my silver, and put it with the second thing from the second chemical. So really I'm taking these two ions up here and putting them together. And notice, even though there was a 2 here, that 2 was because of my strontium. And when I put silver and chlorine together, that strontium's not involved. So the 2 is not going to be involved either. That's a +1 and a -1. So after I clean this up a little bit, then we're going to end up with AgCl. This stuff right here. And then my other product is going to be the other stuff, my strontium and my acetate. Remembering to keep strontium first. It always likes to be in front because it has a positive charge. Leaving spaces. Strontium and acetate is only a -1. So strontium's 2 is going to cross over on it, kind of like what it did with that chlorine. So these are all of my formulas. These are getting a little bit out of hand. Now, balancing it, the only things that I put 2s on as I was writing this out was the chlorine and the acetate. So if I have 2 chlorines there, I need 2 chlorines here, and then 2 acetates there. And I just happen to end up with 2 silvers along the way too, but that doesn't really matter. That's just to keep things balanced. So I'm balanced, I've got a chemical equation. The one thing that people tend to forget is to do our states of matter because it doesn't really say it there. But before you move on to the overall ionic equation, remember that is where we break up anything that's aqueous. You might get to this step and be like, okay, I'm done, and move on. Then you're like, wait, I didn't mark anything as aqueous. What do I break up? So hopefully you remember to go back. The states of matter are very important in this balanced chemical equation. So, like I said, the easy way to do this is assume correctly that these reactants are always aqueous. You can check that chlorine and that acetate on the solubility chart if you don't trust me, but they are aqueous, and I know it is because it mentions that they're solutions. Then I start with those products. Chlorine is in the soluble section, but Ag is one of its exceptions. So this is going to be our insoluble solid. Strontium acetate is in the soluble section, and there are no exceptions. So this is going to be aqueous. So now I have my states of matter. I know what I'm going to need to be breaking up. We gotta write small to fit this all on here. Good luck. I'm going to have difficulty too. But overall ionic equation, this is where we break up anything that's aqueous. So this first thing, silver acetate is aqueous, so I'm going to keep that 2 and distribute that 2 to each of these pieces. That A, more like a Q. So breaking it up into silver and 2 acetates. C2, H3O2. Giving it its charge, and then it's aqueous. Strontium chloride is also aqueous, so we got to break it up. But because I have those charges up there at the top, I don't have to rethink it every single time. You can trust them and just follow that through. Here, remember that 2 that's on that chlorine has to come to the front because it's not part of a polyatomic. Okay. Ooh. Clean that up. That's my reactants. Now I need to do my products. And luckily for us, this AgCl, and every reaction will have one, is solid. So I do not need to break it up. This is going to be 2 AgCl solid. And then I'm going to make that a little smaller. I've got one more aqueous thing to go. So I've got this strontium with its +2 charge. That's aqueous. And then there's 2 acetates there. So 2 of these acetates with their -1 charge and that aqueous. So there we go. That's our overall ionic equation. And as much writing as it is and as little fun as I had doing it, it wasn't really that bad as long as I remember how to break things up. So next step is to split this up and kind of classify our, find our solid, of course, first of all. And that should be easy because it's the only thing that's together. Find the pieces, the ions from the reactant side that I needed to make that. And that's going to be my net ionic equation. Everything else, these stuff on both sides, are going to be my spectators. So let's get that broken up. You can probably just copy that straight in. I have to go to the next slide, so pause it if you need. But I'm going to rewrite it here. We had that 2, that's not very visible. There's 2 Ag + 1 aqueous and 2 chlorine -1 aqueous, making 2 AgCl solid. Now, one thing that you might have seen and written down in your instructions earlier that I didn't mention in the first example because it wasn't necessary, is that once you have your net ionic equation, it needs to be reduced, just like any other equation. Technically, we balanced the equation earlier, but when this full reaction happens, this will happen kind of twice, but the true answer is going to be the most reduced form. So we're going to just get rid of these 2's because there's 2's in front of everything. Technically, we don't need 2's in front of anything. They can all be 1's or technically blanks. So this is our final answer for our net ionic equation. And then the rest of that stuff that we didn't include, that acetate, that I finally got the formula right on again, and our strontium. And it doesn't really matter how many of these there were up there. I know technically there was 2 acetates, but we just care about the fact that they were our spectators. So that's our problem. That's our example. And if you're not explaining it or waiting for me to work it out, you could probably do them a lot quicker than I did because each step is really kind of pretty basic. So just get the steps down and how to do them. So you have 3 questions to do on page 11. You'll notice that questions 3 and 4 don't specifically set up each of those steps in their own space, but I'd recommend that you do set them up just like we have been doing. Your personal preference, but make sure whatever you do, it's organized because everything is worth points. I need to be able to see it. And then question number 3, I believe, is the only one you should have to reduce. So check your answers with mine. Let me know if you need any help. Good luck.